Hello, everyone. Thanks for joining my talk. I'm Chao from Intel. So my talk is shared device assignment. It has 4 parts. First, I will start with some background. Specifically, I will give a definition of shared device assignment, and then explain in detail our motivations, for example, why we're doing this work and why it is important. And then I will talk about the problem and solutions, as well also page shared to private conversion. This is unique to confidential VM. Actually, it imposes some unique challenges to device assignment. I will share this a little bit and then introduce the solution, which is the so-called coordinated shared private page conversion. Then I will talk about the status and our future work, and then I will conclude the talk with a quick summary. So first, what's shared device assignment is still about assigning physical device to confidential VM and allowing the device, the VM to access most of the MIO and the DMA without host involvement. But the device can access shared memory only. So that's why we have a shared in Islam. So it's to differentiate it from the upcoming trusted device or secure device assignment. So in that case, the device can access private memory. So we are from Intel, and we're working on TDX, but this feature is a common feature for confidential computing implementations. For example, TDX, SE, VSMP, and the CC. Actually, so AMD folks and ARM folks joined the discussions in the mailing list and reveal our patch. So we together shipped the solution into its current form. So to further illustrate the shared device assignment, we can look at 3 different IO models for confidential computing. So on the left side is the emulated case. So in this case, you generally have a device backend in the user space. It will emulate MIO and DMA from the confidential VM. It can only access the shared memory, and in most of cases, it will translate the GET request to some host operations. And shared device assignment, you assign the physical device to the confidential VM, and the device can only access shared memory. The case on the right side is the trusted device assignment. In some cases is also called as TIO. So in this case, you assign some trusted device to the confidential VM. And the device can access private memory. This needs some hardware support and firmware support, also OS support. So it's, I think it's not already available. So why we are doing this work? So first is we want to support device assignment to improve the I/O efficiency in the confidential VM. So this slide is actually from GTC 25. It's a GPU pass-through. And so, as you know, some GPU models suppose confidential computing mode. With this mode enabled, so the confidential VM can establish some encryption key with the GPU, and then it can encrypt its data and put it in the shared memory. Then the GPU can read the encrypted data and decrypt it and process it. So in this way, so the data you shared with the GPU and some model IPs are secured, so not accessible from the host. So the other reason why we're doing this work is for TIO. So the question we got is that TIO is something much better, so why you are doing this work? So the answer is quite simple, because TIO won't replace shared device assignment, and instead is something built on shared device assignment. So as you can see on the left side, this is the secure device state machine. This is defined by the PCIe TDI-SP spec. So this is one of the building blocks of TIO. So according to the spec, so a device starts its life in the config unlock state, and it can move to the lock state and then to the run state. And at runtime, if some error occurs, then the device moves to the error state. So in both config unlock state and the error state, the device can only access shared memory. So it works in the shared mode. And so when we try to enable this feature, I think there are two options. One is we assign device in unlock state to the guest. The other is we assign a device in locked state to the guest. But if the device is in the locked state, it means the guest firmware and the guest OS can change its configuration. So, but you don't know if the guest firmware or the OS is some legacy software stack. So it may be not prepared to handle device in such state. So for compatibility reasons, so the decision is that devices are assigned to guest in the shared mode, and the guest coordinated the transition into private mode. So, and also the ability to operate the device in shared mode is also prerequisite for private memory, private operation recovery. So this is our long-term goal. Yeah. So this part is problem and solution. So why device assignment can work as is for confidential VM. So first, a recap of memory encryption state. Confidential VM has both private memory and shared memory. Private memory inaccessible from the host or device. This is the default state of memory for confidential VM. And the shared memory is accessible from the host or device and should be mapped in IOMMUFD DMA, because guest may use any shared memory for DMA, so you should map all the shared memory in IOMMU. And another way to translate page between shared and private. This is generally done by a HAP call, and guest does this, for example, when it allocates buffers for SWIOTLB or some drivers inside guest call some DMA coherent API, or for some pivot features. And this conversion request is handled in the QEMU. In general case, QEMU will discard the existing mappings and then set memory attribute to private or shared. So what are the problems? The first problem is for legacy VM. If we have a device assignment, the QEMU will map all the memory. Will do DMA map for all the guest memory, and this will calls all the memory allocated and pinned by VFL. So in confidential case, I think the operation is useless because all gathered memory is private for confidential VM at VM startup. So in this case, so all the shared memory are allocated but unused. So this causes 2x memory consumption and boot time slow down. And the other problem is IOMMUFD mappings become stale after page conversion. So when you convert page from shared to private, shared pages are discarded from CR3 page table or EBT page table, but the IOMMUFD still pins the shared page. On private to shared conversion, then the new shared page are allocated. So the confidential VM will write to the new page where the device will read or write data from the old shared page. So device access the wrong page to read write data. So the guest and the device can share data with each other. So you cause some function problem, yeah. And so what are the requirements here? So we need to set up and update the DMA mappings along with page conversion. Specifically, we don't do DMA map and pin gather memory at VM startup, and we need to map shared pages into IOMMUFD on private to shared conversion, and the unmap shared page from IOMMUFD on shared to private conversion. So fortunately, we don't need to do this from scratch because virtio-mem has similar requirements for memory hot plug and unplug. So how virtio-mem solve this issue? So it's used a mechanism called RamDiscardManager. So this infrastructure is introduced by David Hildebrand. It coordinates memory hot plug and unplug between many QEMU components. So it tracks private and discard state of guest memory, and it allows VFL to register some callbacks. So on memory plug and unplug, so it will invoke VFL's callbacks to update the DMA mappings. They also support some replay operations because if memory is unplugged, actually, so during VM migration, you don't need to migrate the page to the remote host. So through this replay operation, you can skip discarded memory. Yeah, so currently it has only one user. It's a virtio-mem device. So what's our solution? Our solution is to extend this RamDiscardManager to implement the so-called coordinated page conversion. So first we introduce this RAM block attributes to manage the discard and populate status of a shared page. So the structure definition is below. So we have a bit map, and we also have a RDL list to allow others to register their callbacks here. And on RAM block creation, we instantiated the RAM block attributes for gather memory FD back at the RAM block. And the VFL registers callback to this new RAM block attributes. And on page conversion, we will invoke VFL callbacks to update the DMA mappings. So on private to shared conversion, we notify verify that some shared page is about to be populated. So you need to map them. And on shared to private conversion, so we notify verify that some shared page is going to be removed. So you need to remove them from IOMMUFD mappings. And so then our status and some future work. So we send out 7 versions. The version 7 got merged in QEMU v 10.1.0 RC0. And we just did the bare minimal work and some future work. For example, we need to support large pages in IOMMU mappings, and we need to integrate this solution with guest memory FD in-place conversion, and we need to add replace support for LAM migration, and also try to make it coexistent with virtio-mem. So I will explain why large page is not supported in IOMMUFD mappings. So first, partial unmap is not supported by VFL or IOMMUFD yet. So what's partial unmap? Partial unmap is, so you have a ROV range mapped, and later on you want to unmap a small range of the previous large range, and then this operation is not allowed. But this is needed for page conversion because current host and guest contract is that page conversion may convert any single small page. So our current solution is we split large IOV range into small pages and do DMA map for each page. So let's avoid partial unmap at the cost of being unable to use large pages in IOMMUFD mappings. So this also makes mapping or unmapping a large IOV range more costly. So the ideal solution is we need to support the partial unmap in IOMMUFD. So yeah, so I think there's some ongoing work. I think from Jason, he tries to add a new cart mapping operation to IOMMUFD. So this new operation will allow us to break large pages into small pages. So when this FC patch gets merged, I think we will add some support in the QEMU side. And another thing we want to do in the future is to extend the status tracking. So currently, the RAM block attributes bitmap only track whether the shared page is populated or discarded. But the private page status is also important because if we want to support LAM migration, so for shared page we just copy in the user space, but for private page you can't just read and write it in the user space. In most of the cases, I think you need to invoke some error control and then call into the firmware to get the encrypted status, encrypted content, and then translate it to the remote host. In this case, the user space needs to know which page is private and which page is shared. So someone may realize we can derive private page status from shared page status. But if we consider memory plug and unplug, so if a page is unplugged, it means both shared and private are discarded. So we can't assume. So if a shared page is discarded, it means the private page is populated. So if in the future we need to support both virtio-mem and the NAM migration, so we need to extend our current status tracking. So we need to redefine our current page status to 3 different status: discarded and shared populate and private populate. So the transition between shared populate and private populate is driven by page conversion, and the transition between shared private populate and discarded is driven by memory plug and unplug. So now we need to rework current callbacks to accept the new status and then handle status changes accordingly. So then the summary. So first, shared device assignment is a cross-vendor solution to enable efficient I/O for confidential VM. Then shared device assignment is the foundation of upcoming TIO. And so the key challenges of shared device assignment support is to update IOMMU mappings alongside page conversion. And there are some future work we need to do. Yeah. So that's it. Any questions?